Hello everyone, welcome to Dakshana classroom programs. In last lecture we talked about surface tension, and in that we discussed about surface energy. So we saw how exactly surface tension ultimately result in surface energy, or what is exactly surface energy. So means there is a free surface associated with the liquid, then there is some energy stored in that, or in simple term you can say if you are increasing the surface area, free surface area of a liquid, we need to supply some amount of energy, and that energy gets stored in the surface and we call that surface energy. Let's see some application, then we will continue with the next topic. So here we have a problem. A film of water is formed between two straight parallel wires. So let's say these are two straight parallel wire 1 and wire 2, and between these two parallel wire a film of water is formed. So this is the film of water, and the length is given as here 10 centimeter. This thickness separation between them is 0.5 centimeter. Yes, 10 centimeter long, and its separation of 0.5 centimeter. Calculate work required to increase the separation by 1 mm. So now we want to increase the separation between these wires. So let's say I want to shift this wire here, right? Simple problem. So this increment is 1 mm. So then what will be the additional work required? So straightforward. So in this situation, as surface area is increasing, is it? So work need to be done. Now work done we can write is equal to delta A multiplied by surface tension. Next thing is, what is the change in area? So change in area will be equal to this much, and we need to count here because film will have two surface, one this side, another back side. So total increase in surface area will be 2 times of this surface area. So this implies I can write delta A is equal to length is, let me write everything here it's given in SI unit, so it's basically 0.1 meter length multiplied by this width, increment is 1 mm, so 1 into 10 to the power minus 3. This is the change in surface area on one side, multiplied by 2, so that will be equal to 2 into 10 to the power minus, this is 4 meter square will be the change in surface area. Then I can write work done is equal to how much? This is 2 multiplied by 10 to the power minus 4 into 7.2 into 10 to the power minus 3, and that comes out to be, this is a 14.1 into 10 raised to the power minus 7 joule. That will be the work done required to increase the surface area by 1 mm, or sorry, increase the separation between these two wire by 1 mm. So I hope it should be clear. Let's see the next problem here. So in this situation, the minimum force in addition to the weight required, so beside weight required to pull a wire of 5 centimeter long from surface of water. So let's say this is a wire which is actually lying on the surface of water. This is lying on surface of water like this. So here you must be understanding now, actually in this situation surface water will be like this, so on right side and left side, basically two, and we need to pull this some force, and that will be like weight plus surface tension force. So it is saying in the question clearly the minimum force in addition to the weight. So beside weight, the minimum force required to pull a wire of 5 centimeters. So length of the wire is given as 5 centimeter from the surface of water at 20 degrees Celsius. So this force required is given as 728 dynes. This is in CGS unit, so we will take everything in CGS. And then it's asking about the surface tension of water. So beside weight, what I can write, the force required to pull will be, you can write F net will be equal to weight plus surface tension if it is T multiplied by its length, let's say L, then multiplied by 2L, because one L this side, another L this side, so that will be 2L. And it's given actually F net minus weight, that can be written as T into 2 into L, or 2TL. And this is given as, beside weight, this is given as 720 dynes. So that I can write 2 into L is equal to 5 centimeter multiplied by T, surface tension in CGS unit. This is 728 dynes, and this implies T is coming out to be 72.8 dynes per centimeter. So that is the answer, easy straightforward answer for this problem. So hope you are understanding this. Let's see more problems. Okay, let's see next problem. A thin metal disc of radius r float on water surface and bends the surface downward along perimeter, making an angle theta with the vertical edge of disc. We need to understand the question here, actually what it's saying. So here a disc is there, and it's like a thin disc like this, and it's floating on the water surface such that metal disc of radius r float on water surface and bends the surface downward. So means the water surface is bent downward little bit like this, and surface bends the surface downward along perimeter, making angle theta with the vertical edge of the disc. So vertical edge of the disc is this, and this is making angle theta. Okay, this is the condition given. If the disc displaces a weight of water, so means buoyancy force will be acting. So on this it will have some buoyancy force. Downward it's mg, or let me write weight of the, okay, mg of disc, and then okay, and surface tension of the water is given as T, then weight of metal disc is, so mg value you are asked to find. So first thing is here surface tension will be acting in this direction, and here this is the angle theta. So it will have two components, one along this T sin theta, another along this T cos theta. You must be understanding that this T cos theta will be helping in its way, balancing its weight. So net upward force by surface tension, that will be equal to surface tension multiplied by total length. So that is equal to T cos theta multiplied by its radius is given as r, so it will be multiplied by 2 pi r. This is the upward force, and here I can now by equilibrium we can write T cos theta into 2 pi r plus buoyancy force is balancing weight of the disc, and buoyancy force is given as, that is equal to weight of displaced water, and which is given as W. So I can write weight of disc is equal to W buoyancy force plus this, that is 2 pi r into T into cos theta, and this will be the answer to the problem. I hope it should be making sense to everyone. Let's see the next case here. So radius of soap bubble is r. So we are having already a soap bubble, and its radius r, surface tension T. Then without increasing the temperature, how much energy will be needed to double its radius? So we are now making its radius double. Let's say this is now radius is made double. It's made 2r. Surface tension will be still T. You must be remembering that surface tension does not change if we are increasing the radius. It is simply a property of fluid. So in this situation, how much like temperature is also remaining constant, then how much energy will be needed? So means energy needed will be to increase the surface area, because surface energy will be stored. So we can get the energy needed will be equal to energy required to surface area, or that you can write delta A multiplied by surface tension. And what is the delta A? So initial area, it is equal to 4 pi r square multiplied by 2, inner area and outside area. Final area is, radius is becoming 2r, so 4 pi 2r whole square, this multiplied by 2, that is equal to 4, and so this is actually 8 pi r square, and this is coming out to be 8 into 4, 32 pi r square, right? 8 multiplied by 4, that's right. So change in area, delta A is equal to minus A initial, that is equal to 24 pi r square. So this is the change in area. Then work done or energy required, you can write 24 pi r square multiplied by t. This will be the answer to problem. So you can see here things are not complex actually. If you have understood the concept easily properly, then things are easy and straightforward. You just need to apply them properly and do the calculation also, like without doing any mistake. You will get straightforward answer. So these are all about basically surface tension, surface energy. Let's continue with the next topic, that is shape of meniscus. Okay, so next is shape of meniscus. Meniscus basically it's you can say free surface. Free surface I already defined. The surface of liquid which is in contact with the air on one side, we call that free surface, or you can say the top layer of the liquid. So I don't know whether you have observed it like with some attention or not, but the point here is that if you look for some liquid, is it in some capillary, one of the example is thermometer, is it mercury thermometers are there. Have you ever observed at the top surface of the mercury, it's like this is the thermometer. So there are actually different possibilities. One is like this tube and mercury is in this shape, or another maybe like it's in exactly flat shape, and another case it's maybe in this shape. If you look at it and if you remember the things from the mercury, actually the shape of mercury in the glass tube or thermometer tube is in this shape. So this is this top surface, basically we can say the free surface, is it, that is also called meniscus actually. So the shape of meniscus, what is like in some liquid the shape is like this actually, curved upward. In some cases it is flat, in some cases it is curved downward, or you can say concave upward. This is convex upward, and this is flat. So the point here, like this is all called meniscus, or you can say shape of meniscus. The point is we need to understand that why this is different in every case, and can we comment then in which condition the shape will be like this, like this, and exactly on what factors this shape of meniscus depends. We know like liquid, because whatever the like container you are filling with the liquid always simply acquire the shape of the container. But if you look at the surface or top surface or the meniscus, then it will be different orientation. Now the point here we need to understand that exactly on what factors this shape depends, and how can we comment that in which case it will be what and why, like what is the science, what is the physics behind this different types of shape of meniscus. So let me explain you. So shape of meniscus, you can say it is the shape of, you can say, top surface of liquid in capillary. and it can be in different possible ways, right? And the reason behind it, why, so what happened actually, let's consider this is a container and some liquid is filled in it. Actually at this end also its shape will be like influenced by the pair liquid and this material of this container, but here because the surface is like quite large, so the shape will not be that much like influencing, we will not see that much like clear, is it? But if we are submerging a capillary here, then it seems exactly like clearly, like we can see the difference. Either it will be like in this situation it will be like this, or it may be in this situation. This rises sometime and it fall also, we call that capillarity action. We will come to that point also in some time only. So before that I am just interested in knowing the shape. So what happened actually, let's say this is the condition, then let's look at it at like molecular level, is it? So what will be the situation here? Let's say this is the capillary and let me consider only this is your liquid, right? So here what will happen, there will be some molecules of capillary or glass and some molecule will be here liquid which will be in contact. If you look at it further, zoom, is it? So let's say this is the capillary and this is the atom of capillary and this is the atom of liquid or liquid molecule, and here you can say this is glass tube molecule. Then there will be adhesive force between these two, and adhesive force, let me calculate or let me talk about adhesive force between these two molecules on the liquid. It will be in this, so this will be adhesive force, right? Because liquid molecule and capillary glass tube molecule, they will be applying force and that will be like in this direction, attractive force. So the force on liquid molecule which is in contact with the wall of the glass tube or capillary, that adhesive force will be directed in this direction. It will also have some weight that will be directed downward, but this weight is actually negligible, so we just simply ignore it. And another thing is, on this liquid molecule there will be molecules of liquid on in this complete side, in this quadrant, so all molecule will be applying some force. So because of that, like you can say this will be the what, sphere of influence, so it will be like 1/4 part of the sphere of influence So then all these molecules will be applying force in this direction. So the net force acting on this liquid molecule will be at, you can say, 45 degree. This is F, net cohesive force. Capillary liquid, when it's like capillary submerged, the liquid surface, free surface or top surface have different shapes, orientation may be like this, maybe this. Now we are trying to understand that what will be the exact shape and on what factors this shape depends, how we can decide, is it? So that we are trying to understand. So I just like if we look at it by zoom view, it will be like this is the capillary in contact with the liquid. At atomic level, let's say this is the atom of basically or molecule of liquid, and this is the molecule of glass tube. Both will be in contact. On this glass tube, there will be glass tube molecule and liquid molecule. There will be force of attraction between them, and that will be called adhesive force. So Fa is the adhesive force. This is the force between, or you can write adhesive force on liquid molecule by glass tube molecule. It will be actually like Adhesive force will be also mutual interaction force, and on glass molecule it will be like in this direction, on liquid molecule it will be in that direction. So that's why adhesive force, this is a adhesive force on liquid molecule by glass tube molecule. And FC, this is cohesive force. Cohesive force on liquid molecule in contact with tube, right? So that is the way we understood here. All right, let me draw the diagram. So I hope now you must be clear that why. So ultimately we are having here this situation. This is the capillary. Let's say liquid is filled up to here. So then this is the atom of, and this is the atom of liquid. Liquid molecule, and this is glass tube molecule. Now adhesive force, now right now I am just interested in talking about net force acting on liquid molecule, is it? So force on liquid molecule, we are interested in that. So force on liquid molecule, we understood one is adhesive force, another is weight, but we are ignoring that, and next will be this cohesive force, and this angle will be also 45 degree, and this is 90 degree. So what will be the resultant of these two forces? I can write the resultant will be somewhere here. This is resultant force, maybe this angle is some alpha, right? Clear up to here? Then what, from this relation, what I can write, tan of alpha will be equal to what? Tan alpha will be like one component of this. You can write this is FC cos 45, and here FC sin 45, and net horizontal force will be FA minus FC this, and divided by the, like this is the vertical force. So tan alpha will be equal to, you can write FC sin 45 divided by FA minus FC cos 45, right? I hope you are clear. This can be, so this is FC by root 2 and this is FC by root 2 FA. So then FA FC divided by root 2 FA minus FC, that will be, this is tan of alpha. Now based on this value tan alpha, is it, if net force is actually like different possibilities can be there. If alpha value is what, 90 degree, then it will be, the surface will be what, exactly flat. It will be like net force will be what, downward, so it will be in flat, and then based on that it will, so by this time you must be clear that what exactly is happening at this junction or at this liquid and capillary tube interface. It's the mainly cohesive and adhesive forces which are playing the role, and the cohesive adhesive force is the property of liquid material, of liquid and capillary tube material, is it? So if these two pairs we are changing, then things will change here. So now finally we got this relation. Let me now, based on these different combinations, let me tell you what will be the exactly angle, and based on that we can say comment on the shape of meniscus also. Okay, so finally we got the relation that this tan alpha is equal to that. So now the first condition, tan alpha equal to FC divided by root 2 FA minus FC. If this quantity is equal to 0, means root 2 FA equal to FC. If this quantity is like this is equal, what it implies, this quantity will be 0, and that this implies tan alpha will be infinite, and this implies alpha will be equal to 90 degree. Clear? If alpha is equal to 90 degree, what it means net force will be vertically downward, and liquid, it can be a normal stress. So in that situation you can write here, this is the capillary then orientation or the shape of meniscus will be plane. So this will be 90-degree angle, and this will be the shape of meniscus. And this is the condition of this example. This is the situation of when pure water is filled in silver coated capillary or tube. And at that situation, the shape of the meniscus, it's simply horizontal, plain, flat surface, right? And here this is the situation. What exactly happened? F adhesive root 2 times F adhesive is equal to F cohesive. Next condition, if this quantity is positive, means root 2 F adhesive minus F cohesive greater than 0. This implies root 2 F adhesive is greater than F cohesive. That implies tan alpha is some positive. Alpha is less than 90 degree, right? Because up to 90 degree it's positive. Tan alpha, that will be like positive. So tan alpha, it's like less than 90, alpha less than 90 degree. What it means there is net force in this direction, right? So here what will happen actually in this situation? Alpha, so the orientation, this is the capillary, then orientation will be in this situation, it will be in this shape, right? And here net force will be like in this direction. This is F net, this will be alpha, so it will be concave upward, right? So the shape of meniscus will be concave upward, and it will be like this. And this is the example, let me tell you that. So this is the case of water in, here example is water in glass tube or capillary. In that situation, the shape of meniscus is like this. And the next case, is the third case, if root 2 Fa is minus Fc less than 0, that implies root 2 Fa is less than F cohesive. This implies tan alpha is less than 0, alpha is greater than 90 obtuse angle. So in this situation, the meniscus will be in this orientation. You can just imagine here, net force will be directed inward. So here in this situation, the shape of meniscus will be something like this. So in this situation, you can see the net force is directed here. So the alpha, this is alpha, this is F adhesive, F cohesive, this is alpha where it's greater than 90 degree obtuse angle. So this is F resultant, and the shape of meniscus will be convex upward. Meniscus will be convex upward, and this is this. So in this situation, what is happening, like here you can say f root 2 time, or f adhesive is less than f cohesive by root 2, you can say. So that is, and here this situation when mercury in glass tube or glass capillary, then shape of meniscus is that type convex upward. So I hope this is all about different shapes of meniscus. So it depending on exactly what is the pair. Remember that because its shape of meniscus is the resultant property of cohesive and adhesive force. So the meniscus shape will depends on the pair of material of capillary and liquid, is it? Shape of meniscus is the resultant property of pair of material, tube and liquid field. When pair is changing, then only it will be changing, is it? So when pair property is changed, then shape of meniscus will change. I mean, like, if you are, let's say, mercury is filled in glass tube, you are filling mercury in another type of tube, material tube, then also it will change. But if you're changing the radius and all that, those things will not result, is it? Because adhesive force, cohesive force, all these things are like remaining. These are properties of what? Pair of material of liquid and glass tube. So until you are keeping those things same, like those things same, the shape of meniscus will still remain same, right? So this is all about shape of meniscus. Let's next talk about angle or contact angle and angle of contact. Okay, so we understood the shape of meniscus and we saw that actually it depends on the adhesive and cohesive force, and adhesive and cohesive force is a property of pair of solid and liquid. So once we are changing the either of the things, or like pair means anyhow it's changing, then it will be like changing the adhesive cohesive force, and that result in different like change in meniscus. So we like next is angle of contact or contact angle, angle of contact. It's also related to shape of meniscus. So what happened actually in case of different pairs of solid and liquid in the capillary, we understood the meniscus shape is in different orientation like this. So here we can say this is the wall of the container, and if I draw a tangent wall of the container and tangent to the free surface, this is the tangent to the free surface at point of contact of these two, this is point of contact, then there are two angles possible actually between the one is this, another is this, let's say theta 1 and theta 2. So the angle which is lying inside the liquid is termed as angle of contact. Similarly, in this case, if the meniscus is convex upward, then this is the wall of the container and tangent to the free surface is this, then this will be like theta 1 and theta 2. So the angle which is lying inside the liquid is which one? Theta 1. So theta 1 is termed as, is called as angle of contact, is it? So angle of contact, it is defined for a pair of solid capillary wall and liquid, pair of basically solid, that is capillary wall, and liquid, pair of solid and liquid, such that it is defined for A and it is equal equal to the angle between wall of capillary and tangent drawn to the meniscus, or you can say the free surface. And there are two angles lying in this situation, theta 1 and theta 2. The angle 2, okay, you can write 2 angle will be formed, then the angle lying inside the liquid is called as angle of contact, right? So in this situation here you can say one is theta 2, wall of the container, tangent to the free surface at the point of contact. So two angles are possible, theta 1 and theta 2. The angle which is lying inside the liquid will be termed as contact angle or angle of contact. So here in above two situations, theta 1 will be the angle of contact. So you can see it will be also depending on what? Cohesive and adhesive force. So in this situation what happened actually here? You can say adhesive force is higher, is it? We can write here adhesive force is greater, then adhesive force is greater, then what will happen actually here? Theta 1 or theta angle of contact will be small when adhesive and cohesive force, or we can exactly also relate it here, net force will be lying inside, is it? If I just relate it with the same condition of shape of meniscus like this, so here this is, let's say, atom, so this is adhesive force, cohesive force, and net resultant force, let's say this is alpha, then we already written tan alpha is equal to what? F cohesive, this is a sine of 45 divided by F adhesive minus F cohesive cos of 45, that finally comes F cohesive root 2 times F adhesive minus F cohesive, is it? We already got. So here what will happen actually when tan alpha, this tan alpha is, I mean, like, alpha is not actually angle of contact, but we can relate it with the alpha angle actually. So here what will happen actually here, if tan alpha, you can write root 2 F adhesive is equal to F cohesive, this implies tan alpha is equal to what? Infinity, and implies alpha is equal to 90 degree. At that time angle of contact is also exactly same. So this case angle of contact theta will be also equal to 90 degree. Similarly in second case, if this quantity is positive, means root 2 F adhesive cohesive greater than 0, F adhesive is greater than F cohesive by root 2, this implies alpha will be acute angle, and in that case alpha will be acute. What will be the situation? So it will be like this situation, like this, and we can write here alpha will be equal to, if we look at it, alpha will be equal to actually theta. So in this situation you can write angle of contact will be acute angle, because this is also related to meniscus. In this situation we already know meniscus shape will be like concave upward, and that is what exactly like in this. So this angle we are defining just as angle of contact, and this angle I will just draw. Okay, so first thing is for a pair of liquid and capillary, the shape of meniscus is in different orientation. We define here angle of contact. It is the angle between wall of the capillary and tangent drawn to the free surface of the liquid at the point of contact. Two angles are possible. The angle lying inside the liquid is termed as angle of contact or contact angle. So it can be 90 degree, it can be obtuse angle, it can be acute angle also. Let me tell you a few more things about. So here we understood, let's say, let me define it, let me consider this case. So in this situation, this is what is happening here. Your net, you can say, adhesive force is, or net resultant force is coming out to be F resultant. This is your alpha, because at this point this will be your F cohesive, that is at 45 degree. This will be at 45 degree. Just 1 second, let me draw the diagram properly. Okay, see, this is the situation actually here. So this is the net concave surface, and in this concave upward, resultant force will be in this direction. This will be your angle alpha. Now this is the horizontal line, so I can write this is angle alpha. This will be what? 90 minus alpha, and because this is tangent, so it is tangent to the free surface, and this resultant force will be normal to that free surface. So means I can write this, and this will be at 90 degree. These two will be at 90 degree. Then this is alpha, this will be 90 minus alpha, and this is also what? Like total is 90, so this will be equal to alpha. So we can write here actually angle of contact is simply equal to angle of alpha. Now in this situation, if this is the condition, F adhesive is greater than F cohesive by root 2, in that case alpha will be acute, and here you can see liquid will wet the surface or capillary surface. And the third case is if here you can write this quantity is less than 0, means F root 2 F adhesive minus F cohesive is less than 0. That implies F adhesive is less than F cohesive by root 2. In that situation, alpha will be obtuse angle, or you can write angle of contact will be more than 90 degree. So these are different possible cases for angle of contact. Angle of contact also must be clear to you, and that is also like related to shape of meniscus. So angle of contact also depends on the pair of liquid and solid, I mean like capillary wall. Few points, let me just write about them, then I will tell you. Okay, a few more points about that angle of contacts. Let me explain you those. First, it does not depend on the inclination of solid and liquid. Means what it exactly saying? Let's say this is a container and capillary is there and some angle of contact. This is the orientation. If this capillary is inclined at some angle, let's say like this. In that situation, on inclining the solid, basically capillary, the angle of contact will still remain exactly same. Angle of contact will not change. That is the meaning of point 1. So capillary, once like it's vertically, if you are inclining at some angle, that doesn't mean the angle of contact will change, because it's a property of solid and liquid pair. When you are changing that solid liquid pair, then only your angle of contact changes, right? Further, next, this relation we know already. So at a particular, means like here, what is the F adhesive? This is basically force between liquid molecule and adhesive, means like solid molecule. What is happening here? Cohesive force between liquid molecule. When we are increasing the temperature, then what happens? Cohesive force decreases, right? Because of that, surface tension also decreases, right? That must be clear. So on increasing the temperature, implies surface tension decreases as cohesive force, you can write, decreases. So if cohesive force decreases, now here you can see what will happen actually here. If temperature is increasing, this cohesive force will decrease. So overall, let's say at one moment of time, this quantity, I am saying this quantity is becoming 0. Okay, now I am saying, so what will be the angle of contact? It will be 90 degree. Now if temperature is increased, what will happen? This quantity will decrease, this quantity will decrease, this will become positive. So in that case, soluble like on increasing temperature, angle of contact decreases. So you can see what is happening here. 90 degree, it will, from 92 it will reduce some positive quantity, and it will be, your alpha will become less than 90 degree, it will be acute. Just wait, I am saying, let's say initially alpha is 90 degree. What it mean? This quantity is equal to this. Now what I did, I just increases temperature. Increasing temperature will mean this quantity reduces. This quantity reduces means overall this quantity will be what? Less than 90 degree. The less than 90 degree means alpha will be acute, means this quantity will be less than infinity. That means angle alpha theta equal to alpha is less than 90 degree. Clear? So that is what is happening, angle of contact decreases. That is what, increasing temperature, angle of contact decreases. Clear? And soluble impurities increases the angle of contact, because soluble impurities actually does what? Soluble impurities increases surface tension. If you remember the things I discussed about variation of surface tension of factor affecting surface tension, that is impurities and temperature, you can connect those things here also. So soluble impurities, they increases surface tension. Surface tension increases means cohesive force increases. So if I'm just comparing the things, initially if this quantity is infinity, means this quantity is 0. So if surface tension increases, soluble impurities means surface tension increases, means cohesive force increases, means this quantity will become negative. That means alpha will become greater than 90 degree, and that's what increases the angle of contact. Similarly, partially soluble impurities decreases the angle of contact. That is also because partially soluble means they decreases surface tension, and that ultimately result in decrease in this, and that result in decrease in angle alpha less than 90 degree. So I hope you are able to connect. So this is about angle of contact, and we discussed like shape of meniscus also. Let's continue from here onward. Just remember the points, these are important, try to connect them, how exactly surface tension, impurities, temperature, these things are related. If you are understanding those things, cohesive, adhesive force, I think you should be in position to answer even like the shape of meniscus, it will be concave upward, flat or convex upward, right? And those things also ultimately connect with the angle of contact. So angle of contact is simply, it is the, if this is the wall of the container and tangent drawn to the free surface, an angle lying which is inside the liquid is termed as angle of contact. So let's continue from here onward. Thank you.